All right, guys, how we doing? Mr. Rushka here. I'm going to start a 45-minute timer, and however much I get through is however much I get through on your guys' snow day, okay? So I just started it. Let's go. Okay, so I want to try to polish off this explanation for the limit definition of an integral, okay? I want to polish it off, okay? So I'm going to go over to this notability file I've made here, okay? What I've done is I've just drawn some random function, okay? Can be anything, okay? Doesn't matter that my fine motor skills are terrible, okay? I can draw any function I want, all right? And then I've drawn two x values, x equals a and x equals b, okay? All right, and I've shaded in the region underneath f of x, underneath the curve from x equals a to x equals b. Okay, let's use a right Riemann sum. Okay, use right Riemann sum. Okay, to find this area. So I'm going to do that real quick. Okay, so let's try 4 subintervals. Okay, let's try 4 subintervals. Okay, so what that means is I'm going to draw 4 rectangles. I'm going to draw 4 rectangles, okay, whose width is, the width's going to be the width of each subinterval. The height is going to be, it's a right Riemann sum. So what that means, it's the right Riemann sum. So what that means is the height of each rectangle is going to be equal to the function evaluated at the right endpoint of each subinterval, okay? So let's think about this. Our interval is from A to B, okay? So the width of our entire interval is just b minus a, okay? What that means is that since we have 4 subintervals, the width of each subinterval is going to be b minus a over 4, okay? So the width, right, each width here, oh gosh, each width is b minus a over 4, okay? This is a width of b minus a over 4. Okay, this is a width of b minus a over 4. This is a width of b minus a over 4, okay? All right? So that's the width of each subinterval, okay? That means this x value here, the x value at this point, okay, I'm like waving my pointer all around it, okay, is going to be a. So here's x equals a. If we go to the right by b minus a over 4, this x coordinate is a. I'll do it in red. This x coordinate is a plus b minus a over 4, okay? If we go to the right by b minus a over 4 again, this next x coordinate is a plus b minus a over 4 times 2. And then that next x coordinate would be a plus b minus a all over 4 times 3. Okay? So good stuff, okay? So for each rectangle, right, a rectangle area is going to be its width times its height. Okay? So then the total area is going to be the sum. Total area is going to be the sum of the rectangle areas, okay? All right? So let's think about this, okay? So this first rectangle here, right? Let's finish drawing it first of all, sorry. Okay? So it's a right Riemann sum, so I'm going to draw up from that right endpoint of that first subinterval and over, okay? And then down, okay? So that height, the height of that rectangle, right? That's right here. That's going to be f of that x value. So f of a plus b minus a all over 4. Okay? That's the height of this rectangle. Okay? So this height here is f of a plus b minus a over 4. Okay, the width, again, we were saying earlier, is b minus a over 4. So the area of this rectangle, the area of this first rectangle is b minus a over 4 times f of a plus b minus a all over 4. Okay, all right. Good stuff. Okay, let's do that second rectangle. I'll draw that second rectangle. Let's do that in like purple. Okay, second rectangle, if we draw that, all right, we're going from the right endpoint. Okay, so its width, again, sorry, this is kind of a lot in this drawing. Its width is going to be b minus a over 4. Its height, right, we drew up from this x-coordinate, the right endpoint of the subinterval. Its height is going to be the function, the value of the function when we plug that b minus a all over 4 times 2 into it, okay? So that next rectangle that we're going to add to the total sum is b minus a over 4 times f of a plus b minus a over 4 times 2, okay? Likewise, if we were to draw this third rectangle over here, okay, if we were to draw that, we'd have a height of b minus a all over 4. And then that height would be the function evaluated at b minus a all over 4 times 3. So that third rectangle, and I'm going to be kind of sloppy here, sorry. Let me get rid of these two. That third function, or that third rectangle area is going to be b minus a over 4 times f of a plus b minus a all over 4 times 3, okay? And likewise, if we did a fourth pink rectangle, all right, if we did a fourth pink rectangle, the area of that would be b minus a over 4 times f of a plus b minus a over 4 times 4, okay? So this sum right here, this sum right here, right, that would be our estimate, our Riemann estimate of the red area using 4 subintervals, okay? All right, so now let's repeat this, but instead of using 4 subintervals, I should probably leave that up there, right? If we were to use n subintervals, if we were to repeat that process, right, the more rectangles we draw, the more rectangles we use, the better the estimate is, okay? Okay, so let's say we used n subintervals without specifying what n is. So instead of using 4 subintervals, we're going to estimate the area, okay? Okay. So again, right, the total width of my subinterval, we're doing an interval. The total interval is a to b, x from a to b. Okay, we're going to do a right Riemann sum, okay? The total width of the interval is b minus a, okay? And if, just like when we divide it into 4 subintervals, the width of each subinterval was b minus a over 4. Now the width of each subinterval is b minus a over n, because we're using n subintervals, okay? So that's the width of each subinterval, okay? Likewise, the height of each subinterval, right? So the right end point of that first subinterval is going to be a plus b minus a over n, just like we saw up here with 4. Okay, now it's just n, okay? The height of that first rectangle is going to be the function evaluated at that x value, okay? Right? The height of the second rectangle is going to be b minus a over n times 2, plug into f, okay? The height of that third rectangle is going to be times 3, okay? The height of that fourth rectangle is going to be a plus b minus a over n times 4 plugged into f. F evaluated at the x value of a plus b minus a over n times 4. All right, times 5, right, times 6, times so on, okay? So this is going to be, so I'm going to say like just times I right now. This is going to be times the height. The height of each subinterval, okay? All right. All right, so then the total estimate, right, our estimate for the total area would be, right, b minus a over n times f of a plus b minus a over n times 1, right, plus b minus a all over n times f of a plus b minus a over n times 2 plus b minus a over n times, right? So I'm just summing up the areas of all the rectangles, all the n rectangles in my sum times 3 plus dot 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 plus b minus a over n times f of a plus b minus a over n times n. Okay? Okay? All right, guys. So we talked about rewriting sums like this, right, from our dot dot. I like to call this the dot 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 notation because it uses our ellipses, right? We talked about writing expressions like this as and using sigma notation, right? Okay. The only number that's changing in each term is this number right here. That's at the right side of our f number. Okay, inside of our function. Okay, 1, 2, 3, all the way to n, right? So what I told you guys was copy everything down that doesn't change. Okay, we're going to try to write this in sigma notation. Copy everything down that doesn't change. So then f of a plus b minus a over n. All right, and then for the stuff that does change, the stuff that is changing right here, you just write an I where the numbers that change, okay? And then you write a sigma, the letter sigma, okay? Then I equals, that's, okay? Down here, right, we're going to write the lowest number that gets plugged in for this I. The smallest number that gets plugged in for that I is 1. The biggest number that gets plugged in for that I is n, okay? Okay, so here, this is our estimate for the total area using a right Riemann sum with n rectangles, or in other words, n subintervals, okay? Okay? Right? So an integral, though, an integral in calculus, an integral gets the area perfect. It's not just an estimate, it's a perfect, it's an exact number for that area, okay? So how many rectangles do we need to use to get an exact estimate, an exact precise number for that total area? We've got to use an infinite number of rectangles. So the limit definition of the integral is going to be, we're just going to copy all this down. I'll even use the copy function on Notability. It'll be fancy, okay? We just take this sum, all right, and we take the limit as n goes to infinity, all right? That's going to be equal to the exact total area, okay? So I just wanted to clear up what we were talking about the other day. Let's take a little screenshot. Take a screenshot, pause, okay? I wanted to clear up what we were talking about the other day, trying to define these Riemann sums, okay? I'm trying to define the limit definition of the integral, okay? So let's use this. I'm actually going to kind of ratchet here and take a picture with my phone because I'm not going to write this down. There we go. Okay. So let's take that. Let's use that and go back over to the notes. Okay. All right. So I want to do example 7 then. So we're going to use that limit process to find the area between y equals x cubed and the x-axis on 0 to 1, okay? So let's write down that formula from that clip I just showed you. So we're going to do, I'm literally just copying this down from what I wrote on that other slide. The limit as n goes to infinity of the sum from I equals 1 to n of b minus a over n times f of a plus b minus a all over n times I. Okay. All right. Cool. Okay. So now what we got to do is we got to write down what a is, what b is, and we've got to write down what f of x is. Okay. So a is going to be equal to the left endpoint of your interval. Okay. The interval is from 0 to 1. So a is 0, b is the right endpoint, so b is 1. Okay. And f of x, right, that's just equal to our function here. So this is y equals x cubed, so f of x equals x cubed. Okay. Now, okay, first of all, let's plug in our a and our b down here, okay? So this becomes the limit as n goes to infinity of the sum from I equals 1 to n of, okay, that's going to be 1 minus 0 over n times f of 0 plus, what is that, 1 minus 0 over n times I. Okay, so that's the limit. Just going to simplify some of the algebra. Times the f, what is that, 1 over n times I. Okay, all right, let's plug in for f right here, okay? I think we had some trouble with this the other day, right? So f of x equals x cubed, okay? Here's how you plug numbers into a function. If you have f of x equals x cubed, that means f of 1 equals 1 cubed. So anywhere there's an x, you just replace it with the 1, okay? F of 2 equals 2 cubed, okay? All right, f of a, anytime we see an a, or an x, we're going to replace it with an a. F of a equals a cubed. F of x plus h would be x plus h quantity cubed, okay? So the way we plug numbers into functions is we put whatever numbers inside of our parentheses, okay? On the right side of that equal sign here, wherever there's an x, we just replace it with whatever's inside of our parentheses, okay? So x got replaced with x plus h, okay? Likewise, okay, so looking at this guy right here, f of 1 over n times I, what we're going to do is we're just going to, everywhere there's an x, we do parentheses and we put in a 1 over n I cubed, okay? So f of 1 over n I is 1 over n I cubed, okay? So this becomes limit as n goes to infinity of the sum from I equals 1 to infinity of 1 over n, and then I'll even write it down orange, times 1 over n I cubed, okay? Okay, so we're done plugging in all our numbers. Now we can evaluate this sum and slash limit, okay? So let's cube this, okay, and then simplify it, okay? So that's the limit. Then goes to infinity of sum from I equals 1 to n. What is that? 1 over n to the 4th times I cubed, okay? Now I'm going to highlight this 1 over n to the 4th. Notice in this highlighted expression, none of it depends on I. If none of it depends on the variable that's at the bottom of our sigma, we can pull it out. We can pull it out of the sigma. We can't pull it out of the limit. So that's the limit as n goes to infinity of 1 over n to the 4th times sum from I equals 1 to n of I cubed. Okay. All right, so now I've just got to evaluate this sum right here, okay? So let's go up to my pink sheet. Well, your guys' pink sheets, okay? Sum from I equals 1 to n of I cubed is n squared times n plus 1 squared all over 4. Right, and I just got that from my pink sheet. Was that all over 4? All right, so I got that formula from my pink sheet right here. Okay. Okay, so let's simplify this algebra right here, okay? So limit as n goes to infinity of, what happens here? What does this evaluate to? This becomes 1 over n to the 4th times n squared plus 2n plus 1 all over 4, which is n to the 4th plus 2n cubed plus n squared all over 4n to the 4th. Okay, so this simplifies to the limit as n goes to infinity of n to the 4th plus 2n cubed plus n squared all over 4n to the 4th. Okay, so there's that. Now it's just evaluating a limit. This is a pre-cal problem, right? This is the n behavior asymptotes of this function, okay? So as n goes to infinity, right, this limit is going to be equal to 1/4, right? And that's because, right, the degree of our top is 4, the degree of our bottom is 4. When the degrees are equal, we would just divide the lead coefficients to evaluate this limit at infinity. So 1/4, final answer of this problem, okay? So the area, this area equals 1/4. There you go. That's an integral, okay? So what I just did was, what I want you to see is how I apply, this is a generalized definition, limit definition of the integral, how I actually apply that to a specific problem, okay? A specific function with a specific interval, okay? So now you guys know how to find like the area, this little like two-dimensional Hershey Kiss thing. So good for you guys. That's $16,000 put to good use. All right, thank your parents for me. Okay. So that was the big takeaway. That was the big takeaway I wanted to get out of this. Okay. Example 7. Okay. We do example 6 kind of like we did 7, except you don't really have to set it up. You just do the evaluating the limit at the end. Let's do example 8. Let's do example 8. Okay. Use the limit process again. Okay. So our A is going to be 1, B is going to be 2, and then f of x equals 4 minus x squared. Okay. So we're going to start with the limit, start with that formula, the limit as n goes to infinity of the sum from 1 to n of b minus a all over n times f of a plus b minus a all over n I. Okay, that's it. Okay, let's start plugging stuff in. So this is the limit, as n goes to infinity of the sum from I equals 1 to n of 2 minus 1 all over n times f of 1 plus 2 minus 1 all over n I. Okay, that simplifies to, what is that, 1 over n times, it's going to be 1 plus, that's going to be n plus 1 over n, f of n plus 1 over n times I. Okay. Is this supposed to be that hairy? I guess so. Okay. So here's f of x. So f of n plus 1 over n times I is going to be equal to 4 minus n plus 1 over n times I squared. That's going to be equal to 4 minus n plus 1 quantity squared over n squared times I squared. I don't know if I should expand that out yet or not. I'll hold off. So like we equals the limit as n goes to infinity of the sum from I equals 1 to n of 1 over n times, okay, in brackets, 4 minus n plus 1 quantity squared over n squared I squared. Okay. All right. It's going to be easiest to evaluate this limit if I combine this 4 and this fraction right here. So I want this 4 term here to have I want a common denominator. The common denominator is going to be n squared. So I'm going to rewrite this 4 as 4n squared over n squared. All right. So this becomes, so this is a bunch of algebra, guys. Like, you should be able to do this algebra on your own. Okay. I'm just combining these two fractions right here. It's going to give me 4n squared minus n plus 1 quantity squared all over n squared. And then again, there's still an I squared right there, okay? Okay. If you multiply this 1 over n times everything in here, this becomes, that goes away. This just changes to an n cubed in the bottom when you multiply that 1 over n in there. Okay. Now let's expand and simplify all this stuff. So 4n squared minus n plus 1 squared equals minus n squared minus 2n minus 1, which is 3n squared minus 2n minus 1, okay? So this is the limit as n goes to infinity of the sum from I equals 1 to infinity of 3n squared minus 2n minus 1 all over n cubed. All right, and that's times I squared, okay? All right, so again, everything I just highlighted in orange, none of that has an I in it, so we can, and since the variable down here is I, we can pull it out. So this is equal to the limit as n goes to infinity of 3n squared minus 2n minus 1 all over n cubed times the sum from I equals 1 to infinity of I squared, okay? The sum that I just highlighted in orange, okay? You can evaluate that with your pink sheet. You've got the formula for that in your pink sheet, okay? So n times n plus 1 times 2n plus 1 all over 6. I gotta look at it again, sorry. N times n plus 2, okay. Over 6. Oh my gosh, this is filthy. All right. Okay. And then, oh gosh. Do I want to do all this algebra? This is a limit as n goes to infinity. What's the degree of the top going to be? The degree of the top is going to be way bigger, isn't it? All right, what does the answer key say it converges to? I'm going to skip the loads of algebra in the interest of time. Ah, the stuff I forget at school. we go. All right, guys, magic. It all this crap simplifies to 10n cubed minus 9n squared minus n all over 6n cubed. So 10n cubed minus 9n squared. Where was it? Minus n all over 6n cubed. Yeah, magic algebra. Okay, so all this algebra right here, all this stuff simplifies to this, okay? And then that limit again, degree of the top is the same as the degree of the bottom, so that limit is just dividing the lead coefficients. You get 5/3. There you go. Woohoo! Okay. There's another one. That's another big takeaway, okay? All right, how much time do I have left? 14 minutes. Okay, we should be able to get through most, if not all, of the rest of 6.3, okay? So, definite integral notation, okay? Example 9, evaluate the following definite integral using the limit definition, okay? So, this is actually this is literally the exact same as this, okay? What have we been doing? So before we do all of this junk, no, it's not junk, it's awesome. I love it. Before we do all of that, right, what have we been doing? What have we been actually gaining from the problem? We've been writing down A, the left endpoint, B, the right endpoint, and the f of x, the actual function we're doing, okay? Okay. Down here, this gives you the exact same thing in one little notation here. This is called integral notation, okay? What this means is this number on the bottom, this is going to be your A. This number on the top of that little S thingy is going to be your B. And then this function right here is your f of x, okay? But it's the exact same formula, okay? It's the exact same formula. We're going to do limit as n goes to infinity of the sum from I equals 1 to n of b minus a all over n times f of a plus b minus a all over n times I, okay? So again, we really right here, we would just do limit as n goes to infinity, plugging everything in. Plugging in our b's and our a's, we get 1 minus -2, so plus 2 over n times, what's our function? 2x, so times 2 times, what is that? -2 plus, again, 3 over n I, okay? So all the integral notation stuff gives you is this limit, and then we do evaluate it just like we did everything up here, okay? I'm not going to do that in the interest of time, but if you want me to, come outside of class and I can do it, okay? Example 10. Example 10, okay? Set up a definite integral that would calculate the area of each region below, okay? So this is going from the picture to this notation here, okay? So let's write down my endpoints, okay? My left endpoint here is 0. My right endpoint is 5, okay? So my A is 0. My B is 5, okay? What's my function? My function is just the straight line, horizontal line function. So f of x equals 3, okay? So the general formula for how you write down an integral is going to be the little s symbol, and then a integral. This is integral from a to b of f of x dx. Okay. All right. So plugging everything in here for this first one, we get integral from 0 to 5 of 3 dx. That's our answer. Okay. How would I do this one? Okay. Oh gosh. Okay, I'll just call this function. I said oh gosh because I know like 5 different ways to write this down. But I'll call this function. What would that be? Negative absolute value of x plus 4. Yeah, that'd be my f of x. So negative absolute value of x plus 4. Okay. What's my A? What's my leftmost? That's -4. What's my rightmost? What's my right endpoint? 4. Okay. So what we're doing here, right? Let's copy this formula down, okay? So write down the little S thingy, okay? My A on the bottom is -4. My B on top is +4. My f of x is going to be 4 minus the absolute value of x. And put that in parentheses, dx, okay? That's how you do that one, okay? Cool. Sketch and shade the region whose area is given by this definite integral. Use geometry to find the area. Okay, so for this, oh gosh, for these, okay, graph this function, okay? So we should have learned how to do this in Algebra 2, so I'm going to whip through that, or Algebra 1 we should have. So graph that function, okay? All right, graph that function, and then plot, I'll do this in blue, plot these two x values, so -2 and 0, okay? Literally just draw vertical lines from those two values up to the function, and then shade that little like triangle thingy that gets drawn, okay? So that area, right, it's just a trapezoid, right? Two bases that are parallel, and then a height, and then a little slant edge, okay? So that area here would be 1/2 times the length of the bottom, which is 2, times the sum of the sides, which is what? 5 and 1. So 5 plus 1. This becomes a 1, so the area would be 6 here. Cool. All right. So that's how you do those. 9 minus x squared. How do I graph that off the top of my head? That would be what? Okay, I should probably use my graphing calculator. I'm going to cheat, use my graphing calculator. I'm pretty sure it's just, yeah, I don't know. I'm so tired. Whew. Oh, fun. A little semicircle. This is a little semicircle of radius 3. So I'll try to, terrible fine motor skills, but I'll try to draw that as best I can. Oh, look at that. Beautiful. Okay. And then, right, that left end point, -3. Right end point is +3. Okay. Draw lines up to the function. You can't really do that because it's like at the bottom of the function. So the area we want here is a semicircle. Okay. Semicircle of radius 3. Area of a semicircle is pi r squared over 2. Our r here is 3, so pi 3 squared over 2. That's 9 pi over 2. That's our area here, okay? So an integral, so there's a caveat here. When the function is what's called positive semi-definite, so when the function never dips below the x-axis, when it's always above the x-axis up here, the integral is just equal to the area under the curve, okay? Get some water. Okay, and then here, this function, 1 minus the absolute value of x, that's this little like downward facing arrow guy. So graph that function, graph this function, okay? All right, let's plot those two x values, so -1 to 1, okay? So we want the area from here to here, okay? This is a triangle of, so area is going to be equal 1/2 base times height. The base is 4. This is a length of 4. This is a height of 2. Okay, so that's just 4. So that's how you do example 11. Given the graph of f of x below, find the solution to each of the following definite integrals. Use the provided graphs to resketch a graph of the function depicted in each integrand. Okay, so this is going to like back to transformations of graphs from pre-cal. Okay, How much time do I have left? 5 minutes, okay? So I'll start this, okay? Then we'll be done with 6.3. Then we can go straight into how anyone who's not like a very rigorous professor of analysis does integrals, okay? So how normal people do integrals. So we've got this function, okay? They want us to integrate, see, here's f of x. They want us to integrate negative f of x from negative 4 to 0, okay? So where are we going? We're going from negative 4, x equals negative 4, to 0, okay, of negative x. So here's the graph of f of x. If you recall from pre-cal, the graph of negative f of x, we're just going to reflect over the x-axis, okay? We're just going to reflect over the x-axis. So I think I did that right, okay? So what's going on here, so now our area, we're going to draw from our endpoints down to the function. That's confusing. Let me use another color and make it dashed. Okay, so now our area will be this, all the stuff inside here. That would be the area of our integral, okay? They actually want us to find it? Okay, yeah, so they do, okay? So the area of this little quarter circle here, it's a quarter circle of radius 2. So that is what? Pi r squared over 4. So, and it's radius 2, so it's going to be pi. So the area of this guy is pi, okay? Area of this little triangle here, what's that? Right triangle, the base is 2, the height is 1, so 1/2 times 2 times 1 is just 1. So that triangle there has an area of 1, okay? So the total area here is pi plus 1. Now, here's the little caveat, right? Remember my caveat I told you up here, right? An integral is equal to the area under the curve as long as the function never dips below my x-axis. Well, what's it doing right here? What's my red function doing? It's below the x-axis the entire time. So what's going on here is an integral, okay, what's going on here, since all of the function area is negative, the total area is pi plus 1, but since we're always below the x-axis, the answer to our definite integral is going to be negative pi plus 1, okay? So the best way to think of integrals is taking like the sum of a function. So we're summing all the values of negative f of x as x goes from negative 4 to 0. We're summing all of those up, okay? Since for negative f of x, it's always negative from negative 4 to 0, we're summing up a bunch of negative values and a bunch of negative numbers. So our answer's going to be negative, okay? All right, I'll stop there. I'll finish these last few problems the next time I see you. There's a bunch of 6.3 homework assignments. What I'm going to have you guys do, you guys thought you could escape the mini quiz, but you can't. So I'm going to have you guys do the mini quiz as a take home today, and then also do the 6.3 homework for Thursday. And then remember, the packet's due Friday. I already gave you an extension over it. None of you guys have been coming to office hours. I told you to come to office hours. I told you I was going to be bored. That's why I signed all of it for accuracy, okay? All right, I'll be on Zoom from, I'm thinking 9 a.m. to 3 p.m. So if you guys are lost, confused, stressed, worried, hit me up, okay? So send me an email, and I'm going to send out an email too with my personal meeting ID for Zoom. You guys can hop right on. We can talk about this stuff, okay? You guys take care. Be safe.